Okay, 4.3, here's my take. If you see y varies inversely as anything, or as versely as x, or whatever, with that inverse variation, the quick take on it is that means that the x and the y are always going to be timesing to the same answer. And so, if we had x and y always timesing to the same answer, the next thing they tell us is that if x is 3, then y is 5. So we'll just say that. If x is 3, then y is 5. And we know that they times to the same answer all the time. And what's good about that is when they tell us an x and a y together, they actually tell us what they times to. So we don't even need to just quote the whole thing about same, because 3 and 5, they times to 15. And so what that tells us is we got ourselves an answer. Y varies inversely as x, that means that x and y always times to the same thing, always. And then when they tell us that 3 and 5 are the x and the y that are matched up, that tells us what that thing is that's the same all the time. The answer is 15 in all the time to their times problem. And that's the perfect setup, because now that we got that they always times the same thing, we'll just cling to that and we'll say x and y, they times to 15 all the time. So figure out what they times to and then just stick to that. And now we say, okay, they're going to finally ask us a question. They will ask us something about, where'd you go? It just looks like I landed on the same colors before. They're saying, find y when x is 7, and that'll work out. But the only thing we know about it is that no matter what, when I times the two, I'll still get 15, because they always times the same answer. So I'll say, no matter what, it's always going to times to 15. And then whatever they ask me, I can figure out. So they say x is 7 this time, I'll put a 7 for x, and now I got to figure out the y that goes with it. But I know that when I times them, I get 15. And so we'll stick with that. I get 15 when I times them, and now we just got to solve it out. But you know how to solve that. Algebra style, we'll divide out the 7, and then y equals just 15 divided by 7, I guess, whatever the heck that is. You just put it as a fraction, 15 over 7, it should work out. Boom. Now, a particular application of this kind of stuff comes to be like when you move closer to or farther away from a sound. And so the loudness of a sound in decibels is inversely proportional to the square of the distance, inversely proportional to the square of the distance from the source of the sound. Without making a long story of this is a quick take. We'll say essentially this is an inverse variation, but we don't get to say exactly just the distance. We say the square of the distance. And so what that means is if I take loudness L, they say loudness L, varies inversely with the distance, we would say loudness times distance is always the same thing. Only thing difference here is this is the square of the distance, and so we'll say loudness times the square of the distance, or put a d squared is always the same. And this is how loudness actually works here. And so this is something you can cling to even if you take it into a science class, or if you're just doing weird experimental things outside with sound and moving around and stuff. This is sort of a reliable finding. Anyway, for now, we'll also say, okay, we got to answer their questions, Here, let's erase some of that mess. That's not an eraser. Let's erase some of this mess. Okay, they're going to ask us now, if a person is 14 feet from a jet ski, okay, it is 95 decibels loud. Okay, they're telling us, once again, just like when they give us the x and the y makes 15 before the 3 and the 5, they're telling us kind of a baseline of something that they have measured so far. From 14 feet, you got 95 decibels of loudness in your ears. And so then they'll ask us something about it. But what that tells us is if we have a 14-foot distance, then that means D is 4. Why did I put 15? D is 14 there. And then the loudness is 95 decibels. And so 95 for the loudness. And then we'll just make sure that we're square on this. Check this out. We'll say 95 times 14 squared. Don't forget about the square of the distance. Equals same thing all the time, and that's where we get to figure out what it is, because we can run these numbers. This is just like when they gave us 3 and 5. So 14 squared times 95, that'll be a giant number. 14 squared is 196 times 95. I feel like that'd be fun to do in my head, but we're not going to do that. That's 30, and then 9 times 6 is 54, and so 57, I think. And then this is getting boring. I'm going to pause this for a second so you don't have to listen to it. Okay, after the pause, 3 hours later, we have 18,000 and some change. See where I didn't even bother to do it. Okay, so 18,000 and some change ends up being our total, 18,620. That's the total that it's always going to be. And so then when they ask us what they're going to ask us, we can answer it. They're saying now, how loud is this jet ski when the person is 50 feet away? And 50 feet away is a distance, so we'll put that in for distance D. And so back to the old distance mess. D was the distance, and that's the one that you square. We'll put in 50 there. So now you have 50 squared times some loudness that we got to figure out, because we're trying to figure out how loud is it, equals still all the time 18,620 now that we figured that out. And now we just kind of figure them out, and solve out for loudness. And so 50 times 50 is 2500, 2500 times some loudness equals 18,620. And then we'll just divide out the 2500 and you get yourself something, And so I'm not sure that they programmed this one, but essentially we'll say if I divide out by 2,500 on both sides, you can either leave it as some bizarre fraction, 18,620 over 2,500, and maybe hope to reduce it a little bit, or else maybe to experiment with trying it as a decimal. It'd be cool if it actually went in there. Actually, that'd be even better, but it probably won't. Anyway, so you can shove that in there, or else it'd be nicer to understand if you actually just divided the thing and get a calculator out and do 18,620 divided by 2,500, and you get something rounded off or whatever, that'd be nice. I don't see where it says where to round it off to, though. I don't know, experiment with that. You might have to leave it as a fraction. Now we're back to solving equations, no more application stuff, it's just back to algebra. And so with these things, there's always, if you have a rational equation, my favorite take is the old Abraham Lincoln theorem, which is to say, well, don't look it up as that. That's not a real name, but which is to say, if we get the bottoms to match, then, so you look at all these bottoms. If we can get all these bottoms to match, now that I've made that 1 into a 1 over 1, then we won't need the bottoms, is essentially the idea. If you get the bottoms to match, you won't need them anymore. We can solve without them, is the quick take. And so if I saw something like this, here, let's erase some of that stuff. This is going to be my take on it. And again, this is without showing you all the details of why this works the way it does. But this is just, if I were to see this, here's my take, And so to get these bottoms to match, I'm looking at X here. Doesn't have a 3, so I give him a 3. So then he'll be a 3X like this other guy is, And so don't forget to times it on the top as well, times 3 there. This 3X in the middle already is a 3X, so he doesn't need anything. And then the 1 don't got nothing, so we'll times it by a 3 and an X. And now everybody on the bottoms has a 3X. That's 3X, this is 3X, and then 1 times 3X is 3X, so all the bottoms match. And once the bottoms match, we don't need them. We'll just get rid of them. Not because it's magic or anything. Because, really, if you wanted to, we could explain it by saying if you wanted to, you could, at that point, times both sides by 3X. And then they'd start canceling the bottoms of all the fractions out distributively. It's whatever. For that reason, or, there's other perspectives maybe. Then we'll just say if the bottoms match, we don't need the bottoms. And we'll just focus on what the top's got to offer. And so the top over here on the left-hand side is 3 times 3, so that's 9, equals 6. Minus of 1 times 3x is just 3x. And then we'll just solve that out, Maybe get the x by itself. Be careful when you do, of course. Solving maybe minus the 6 over, or you could move the 3x if you don't like it to be negative, etc. But solve yourself until you get an x by itself. Something similar here. Same idea would be, it's just harder to get the bottoms the same because this one's an x plus 1, and that one's just a number 2, and it's weird. This one, though, on the 3 part, I feel like we could make that work better, because we could say if I took out a 3, then the leftovers would be x plus 1, and that's good for us because then that bottom's almost matched because this has an x plus 1 just like that does. And then the only things that are left to figure out are, well, of course, the middle is going to need an x plus 1 as well. But then we have just some numbers floating around, like there's a 2 here that the other ones don't have, and there's a 3 here that the other ones don't have. So we'll make those things happen, and we'll just keep going until they all match. Matchy, matchy. And so then, let's see here. If I had a 3 and an x plus 1 on the right-hand side here, I could times it by the 2, and then I have all 3 of everything. I have the 3, I have the x plus 1, I have the 2. I have everything that everybody has on the bottoms, and this times it on the top as well. And then in the middle part, this guy has a 2, but he don't have a 3, and he don't have an x plus 1. And so we'll give the top there a 3 and an x plus 1. Hey, that's what it's supposed to say, a 1 there. I don't know. And then on the left-hand side, this one has the x plus 1, but he don't got the 3, and he don't got the 2, so we give him a 2 and a 3 on the top as well. A 2 and a 3. It's supposed to say 3. I don't know. We're working on it. Anyway, from there, now the bottoms match, because each one of them has a 2 and a 3 and an x plus 1, a 2 and a 3 and an x plus 1, a 2 and a 3 and an x plus 1. It's whatever. And now we'll just deal with the tops. So here we go. With the tops only. Now we got, on the left-hand side, we have a 2 and a 3 and a 4. That's 2 times 3 times 4 is 20. I was going to say 12, but it is not 12. It's 24, I guess. There you go. 2 times 3 times 4 is 24, minus of 3 times, of 3 timesing with this other stuff. So feel free to times 3 and 3 to make 9 if you like, but I don't recommend distributing until later on because sometimes these minuses, see the minus there, get left out, and you'll forget that it's a minus distributing, a negative 9 distributing, if you do it too soon. At least you might anyway. And so then on the other side equals 2 times 4, or 2 times 2 equals just 4, and then we'll just start solving this mess out. And so don't forget your equation solving skills, of course, this is 24 minus, and then 9x, and then like minus 9 equals 4, and et cetera, et cetera. Keep going until you got something solved there. And then the only caveat is, like, what I'm seeing here is the only thing would be bad. What if we ended up with the answer x equals negative 1? I don't think that's the answer here, but that would be bad. Because then, imagine if I plugged in a negative 1 into our original equation here. A negative 1 plus 1 over here would make this whole thing undefined. That's bad news. Anyway, so watch out for that kind of thing. Every once in a while you get a no solution because of that. I don't think that's happening here. Oh, no, this one it might, though. I mean, they're saying, does it have a solution? So there's a good chance this one doesn't. And so, let's see, if I were to factor out this one, I'd say like 2 and then x minus 2, and then this one already is an x minus 2, but this 5 is trying to hide there with nothing, and so it has a 1 there, and so I'm seeing there, if I wanted to make the bottoms match, it pretty much is just a 5 over nothing, and so he's going to need both a 2 and an x minus 2 that we'll have to give up, and so the 5, he'll need the 2 and an x minus 2, on the top as well, and then over here he had the x minus 2, but they didn't have the 2, so we'll give him the number 2, and then this one had both of them, so he doesn't need anything, so we won't give it anything on the top either. So let's see how that looks. Now that we figure that out, we've made all the bottoms match. This is x minus 2 and 2, this is 2 and x minus 2, this is 2 and x minus 2, they all match, and now let's make them work. On the left hand side we got an x here, minus of 5 times 2 times x minus 2. Again, 5 and 2, feel free to times those to be a 10, but don't distribute it first because you can leave out negatives on accident that way. I don't recommend it. Equals, and then we have a 1 times 2 on the top here on the right-hand side. And then we'll just solving. and then solve whatever you got. And then they're saying, does it have a solution or not? And you'll say yes or no. And if it's a yes, you'll just tell them what the answer is. If it's a no, then you'll just tell them no. The only thing I'm seeing here is just the same issue as before. Because there's an x minus 2 on the bottom here, if you ended up getting an answer of x equals 2, then you'd be in bad shape, because the only thing that the answer could be is the only thing that the answer must not be, because if you plug in a 2, you have 2 minus 2 on the bottom, and it's undefined, and that's no good. So when they say, does it have a solution, you're going to say yes if it's anything else. But if you see, if it ends up being x equals positive 2, or whatever it is in your version of the problem, if your answer ends up being something that would make it undefined, then you'd say, well, the one thing I got is the one thing I ain't want. And so that's a no solution at that point for our purposes. Something similar here, I won't go over the whole thing, but the idea is that we just got to make these bottoms match. And so this one has an x minus 1, this one has the x plus 3. This one, we don't really know what it has until we factor it. I'm hoping that it's x minus 1 and plus 3. Looks like it is. Minus 1 and plus 3. So it kind of matches the others, but what it means is that we got to give the missing parts to those other ones. And so if this one has an x minus 1, we'll give it the x plus 3, and we'll give that on the top as well, x plus 3. And then this has x plus 3, we'll give it the x minus 1, and then give it the x minus 1 on the top. This one had both already, so he doesn't need anything, so we won't give it anything on top either. That being the case, here we go. On the left-hand side, we have an x plus 1 times x plus 3. We got to FOIL out. That's a nightmare. Equals, and then over here on the right-hand side, we have a negative 8 distributing to our x minus 1, and then a plus of just 8. And then FOIL, FOIL, FOIL. This will be a whole bunch of mess. And so I'm looking at this. It seems like as I start to FOIL this out, there will definitely be an x squared in there. And you know what that means with x squareds. We can't just solve them the old-fashioned way. You're going to have to FOIL this out and get it equal to 0. Eventually, you're going to have this thing where it's like all equal to 0, and then you'll have to end up probably factoring these things out. If it doesn't factor, you can use the quadratic formula, but I'm betting by the time it's all done, you'll get this all zeroed out over here, and then we're back into factors, and it'll be like x plus this, or x plus that, or x minus something, or whatever, and then we'll get 2 answers out of it. And then you might get to keep both answers, or maybe you won't get to keep them both, because remember, you'll get 2 answers from a quadratic. If it's got x squared, you get 2 answers. But there's 2 things that we don't want it to be also. Because notice in here, if I have x plus 3, then I certainly don't want a negative 3 for an answer, because negative 3 plus 3 would be undefined. And the same thing, if I have an x minus 1, I don't want a positive 1 for an answer. So right off the bat, off limits, what we see is off limits. Yeah, let's write it that way, off limits, or whatever. I shouldn't use the word limits here like that. Oh, shoot. Because it means something else in mathematics. Off limits. I keep on messing the page up. Whatever. Is, what do we say? Negative 3 and positive 1. If you get either one of those answers as part of your answers, you throw it out. If you get one and not the other, then you can at least use one of your answers. You don't have to say no solution. It just means you won't have both. Anyway, that's my vision for this one. Something similar here. We don't have to go very far into this one. I'm just noticing that p squared minus 49 will probably factor into being a p minus 7 and a p plus 7. That's convenient. And then let's see here. Okay. Hannah can paint a room in 16 hours. Destiny can paint a room in 12 hours. So Hannah's like faster or whatever. Wait. Oh, no, she takes 16 hours, so she's slower. Destiny is faster because she can do it in 12 hours. It's whatever. But then they're working together, and we have to figure out, like, how in the world long is it going to take, and she started thinking, like, is it 16 minus 12 or plus 12, or, and so it's a little bit tough to figure out at first. But here's my take on it. If it takes her 16 hours to do it, then in 1 hour she could do 1/16 of a room. And then the same thing with Destiny. if it takes 12 hours, then in 1 hour she could do, and then in each hour she could do a 12th of a room. So if we put however much she's getting done in 1 hour, and however much she's getting done in 1 hour, and we'll plus them together, that's how much they're both getting done in an hour. So if I just plus those two fractions together, and you got to make the bottoms match and all that, then that'll tell us how much we're getting done every hour, and then we'll do some kind of a rate and time approach. And so if they're working together, 12 and 16 is their time, but their rate is essentially 1/16 of a room per hour and 1/12 of a room every hour. And so playing the game here for a second, I think 48 is what's going to have to work for these things. So we'll times it by 3 and by 4. And let's see here, that's 3 out of 48 plus 4 out of 48, because this is 3 and that's 4. And so let's just do that and make it 3 and 4 makes 7, I guess. So this is 7 out of 48. That's how much of a room they're getting done every hour. So she does 1/16 of it, she does 1/12 of it. Together, they're doing 7/48 of a room, whatever. But then remember, that's a rate of how fast they're working. This is a rate. And so rate, if we do rate times time, I'm going to put T for time, that'll tell us however much work they're getting done, without going into a lot of detail where that came from. But it's kind of like their distance rate time thing. Anyway, they're wondering how long will it take these things, how much time will it take for them both to be working together. And so we know they're working together. That's where we got the 7 out of 48 from. We're wondering how much time it's going to take. What's not implicit, or what, I don't know, I guess what's sort of implicit, but what's not real obvious here is that we're just saying they're still getting one room done. They're just saying, well, if I were to paint a room, like they were doing. And so I guess that's the amount of work we're looking for, is just one room to get done. And so we're, I guess, summarizing to say, if I were to work, now we're working at a rate of 7/48 of a room per hour times some amount of time. How long does it take? However much time is that going to take until I get one room done? That's the idea. What's cool about that is then it's easy to solve for T, because then you might remember if I have it times by a fraction, I can always just times by the reciprocal, 48 over 7, 48 over 7, and then the 48s and 7s cancel, and then I've solved for time. T for time equals 1 times 48 over 7. 1 times anything doesn't do much, and so it's just 48/7 of an hour is what it comes out to. And then feel free if you want to, you probably have to put it in the computer like this, but if you were to divide that up, 7 goes into 48, that's 6 and 6/7 of an hour or something like that. So almost 7 hours, 7 into 48 is almost 7 into 49. So it's almost 7 hours if they were to do it together. And again, I think they wanted an improper form or something in the homework. Anyway, that's my take on that. Same kind of thing with this one. It's an inlet pipe and an outlet pipe, right? Let's see here. Yeah, inlet pipe. It'll fill an empty pool in 6 hours, but that drain was left open, and so it'll start draining the pool, but it takes it 15 hours, so it drains slower. And so I guess the idea is that there's an oops here, and somebody's trying to fill the pool up with the drain open. Fortunately, it only takes 6 hours when the pool to drain it will take 15, so it's filling faster than it's draining, I guess is the idea. That being the case, though, it's the same kind of thing. We're just saying it's 1/6 of a pool every hour is how fast it's filling up, and its rate of how fast it is emptying the pool is 1/15 of a pool every hour. But since they're working against each other this time, only difference is we'll say I'm going to minus their rates, because it's essentially I'm filling it up this fast, and then I'm taking away some of that water every time I fill it up. So it's kind of a takeaway thing. Other than that, it's just like the last one, kind of minus some, and then we'll do the whole something times time equals one pool filled up. That's kind of my take there. Let's see here. Number 10, a plane can fly 220 miles in the same amount of time it takes a car to go 60 miles. If the car travels 80 miles per hour slower than the plane, find the speed of the plane. We're supposed to find the speed of the plane. There's a tip-off on these kinds of problems here. A lot of info going on. One thing that says it takes the same amount of time, And so remember, if you were to say rate times time equals distance, then we also have that if I were to solve that out for time, you could divide the rate over there, and then we'd have time is equal to the distance divided by the rate. So what we might do here, guys, is since they say it takes the same amount of time, I might define time as being distance and rate, because they don't put anything about time, how much time something took anywhere here. And so if they give us any distance information or if any rate information about how fast things go, then we can use those pieces of information to infer things about time. And since we know their time is the same, that'll be good. That was a lot to say. Maybe here's a quick take on that. Same time means the time for one, I'm going to put time. Time for a plane? We'll call that plane time. Is going to be equal to or same as the car time. And then we'll just fill in what we can. But remember, every time we're trying to fill in time and they don't give us time, we'll give it a distance over a rate. And so let's see how that goes. Distance over rate, get ready for the fraction. For the plane, 220 miles is how far it goes, so that's the distance over some amount of time that we'll fill in. And then, or over some rate that we'll fill in, that's right. And then the same amount of time it takes the car to go 60 miles, that's how far the car goes, that's the distance for the car. And then we're about to solve for rates here, or figure out what we can say about rates, I guess, actually. And so it says the car travels 80 miles per hour slower. And so if that's all they give us for rates, we'll have to work with it. And so if the car travels 80 miles per hour slower than the plane, I guess what we could say then is that the rate of the plane we still don't know. So I'm just going to put R for the rate of the plane. And then for the car, what they say is that it's 80 slower than the plane. And so we'll say, well, if I were to take I don't know how fast the plane's going. So that was R. And then if I take that 80 miles per hour slower, then R minus 80 would be slower than, 80 slower than the plane. And that'll be our rate for the car, I guess. And now we have to find the speed of the plane, whatever that means. Speed of the plane. Remember, that's how we define what we were talking about rate here. So I guess if we can solve for this R here somehow and just figure out what R equals, then we'll be all right. From there, guys, I'm going to give you kind of a basic summary. This ends up being like the other fractiony ones we did. We got to get these bottoms to match, and then we won't need the bottoms anymore. And so to kind of kickstart you, remember, this one has an R on the bottom. This one has an R minus 80 thing. And so we'll say if this one has an R, he needs the R minus 80. And we'll give that to the top as well, R minus 80. This one has the R minus 80. He needs the R, and we'll give that to the top as well. And then the bottoms match. We have an R and an R minus 80 in both of them. Once those bottoms match, we don't need them anymore. We just need the tops. And we have on the left-hand side, that's 220, timesing with R minus 80, equal sign 60 times R, or just 60R, you could call it. And then just see what you can do to solve these things out. Okay, next one. Oh, yeah. Consider the inequality. Woo! Okay. These ones are a little bit easier to do when they're equal to 0, No, I forgot. I thought I had one that was equal to 0, but I guess not. In your homework, you should. And so if you get one that's already equal to 0, go ahead and just, skip to that part of it. But the first effort that we're going to be making is making this thing equal to 0, which is, most of the work here. And so let's see here. If this were to be equal to -3, and I keep saying equal, it's really a greater than, but I'm going to treat it like an equal for now because I keep forgetting to say greater than. Anyway, so I want this thing to have a 0 on the right-hand side, so we'll plus the 3, and that'll cancel out. But we'll have to plus 3 over here as well, and so what that gives you is this weird fraction, and then plus 3, and that's weird, but at least at this point it's greater than 0, and that's good. Because from there, we can just kind of customize this thing and try and put the fractions together. These fractions don't match, the bottoms don't match. So I'm going to give this one an x plus 6 to match on the left-hand side, Now the lefty and the righty both got an x plus 6 on the bottom. And so then this is not time to cancel out bottoms or anything. It's not what we're working on. We're just trying to put the fractions together. And so the bottoms got to match. And so now they both are over x plus 6, because 1 times x plus 6 is x plus 6 over here, Anyway, and then the top, though, is an x plus 5 plus a 3 distributing to an x plus 6, which we got from, like, this part. We had the x plus 5, and then we're timesing the 3 with the x plus 6. Okay. We'll figure out what that looks like, but we know about it that it's greater than 0 at this point, or at least that's what we're attempting to establish more information about. And then from here, let's see here, if that's a 3x plus 18 or something like that, so then x here plus another 3x looks like 4x's, and then 5 plus an 18, because 3 times 6 is 18, plus 5 more is like 23 or whatever, and then we have x plus 6 on the bottom, greater than 0. And so now that this thing is equal to 0, or greater than 0, or whatever, now that we're talking about 0, it's a little bit easier to consider, because now we'll suggest this. Whoa. In order to figure out where this inequality is greater than 0, it's important to figure out where it's equal to 0, and maybe where it's undefined. If it hits any undefined points, those would be critical points to consider. And so remember, if it's equal to 0, that means if I can get the top to be 0, then its thing will be 0. If I can get the bottom to be 0, then it's undefined. So we'll just look at both of those things first before getting to anything else about the whole greater than 0 thing. Let's go ahead and see if we can figure out what makes that top 0 and what makes that bottom 0. And then we'll consider both of those situations. And so the bottom is easier because negative 6 plus 6 makes 0, so I can just see that one. But then if I were to do this one, you're doing the little algebra thing, minus the 23, and we have 4x equals negative 23 here, and then divide to 4. So that's weird, but it's negative 23 fourths, and then this is 6 negative. Now negative 23 fourths, 4 into 23 is almost 6 times its well. That's negative like almost 6. And so what we could say from that, guys, is this. These are the two values that are interesting to us. At negative 23 fourths, this equality equals 0, because if the top equals 0, then the whole fraction is equal to 0. And at negative 6, then our inequality is undefined. And that's going to tip us off to something interesting too. And so let's consider both those situations. But remember the goal in mind. We're trying to figure out what values of x it is for which I can plug in x and get this inequality, the whole thing, to be greater than 0. Not less than 0, not equal to 0, but greater than 0. And so what we found out is if I plug in a 23 fourths negative, it's equal to 0. But what about the numbers around 23 fourths? Do they make it less than 0 or greater than 0? We're not sure, but this is the only place where it's equal to 0. That's what we know. Things around it will not be equal to 0, but they'll make our inequality, or our expression on the left-hand side, either greater than or less than. We got to figure out which is which. Anyway, that's a lot of detail. What I'm going to do from now, guys, is let's go to a different slide, remembering these two numbers. And so, we'll talk about that in a minute. What numbers we got here is, let's look at the old number line. We have negative 6. We have negative 23 fourths, which is actually almost negative 6. And we have all the other numbers on the number line. One thing to notice is that there's no equal to in the inequality that we're solving for. So when we're looking for something that makes this equal to 0, we won't be using any closed brackets or closed circles or anything. There's no equal to involved in this. So this thing is going to be an open circle situation. And I guess without trying to over-explain everything, what we're going to try and do, guys, is we'll plug in numbers that are on different sides of this stuff, because this is the number I plug in to make it equal to 0. But what happens over here? What happens over here? What happens over here? What happens with these numbers that are not exactly 0? If I plug in something that's on the left of, oh shoot, I forgot my negative. It's sort of a star in a way, but I caught it, Anyway, what happens to numbers that are like -7, -8 or something over here? Do they make my inequality less than 0 or greater than 0? That's what I'm wondering, is what numbers will make this thing greater than 0, like we were suggesting, That's what we're shooting for, greater than 0. And so we'll just try numbers on different parts of the number line. Let's try -7, try -7. Let's try also something over here way on the other side. We could try, 23/4, that's almost 6 negatives, so I could try -5, or I could try -4, or we just try, I don't know, a positive number even, anything to the right-hand side. Let's just try number 1, +1, that's good. And then what if we tried something in between these two? I'm going to cheat on that one, because I figure if we can figure out these two parts, then we'll know if this one's applying or whatever. Yeah, that's a good cheater's way. That way I don't have to figure out what the heck is in between 6 and 23/4. That would take a second. It'd be a weird fraction. Okay, so let's try -7 into the original expression that we were dealing with. Not the original, but the one with the 0. It's this one here. 4x up plus 23 over x plus 6. 4x plus 23 over x plus 6. 4x plus 23 over x plus 6. We're going to plug stuff into that and see when it's actually greater than 0. And so let's see here. If we try -7, that's 4 times -7 plus 23 over -7 plus 6, and we'll see what that comes up with. The bottom is -1. The top is -28 plus 23. -28 positive 23 is -5. That's a -5 over a -1. That's a negative into a negative is a positive. So it's +5 over 1. So numbers over here, when I try -7, and numbers that are on this part of the number line with number 7 that are to the left of that -6, seems like they're going to have the property that we want, because this 5 over 1 actually is greater than 0, because it's +5. So I'm going to color this junk in. I'm going to keep that circle open, because we never include the number that made it undefined. So that's open circle. Anyway, that means everything to the left is going to work out. My bet then is that nothing here in between will work out, but then everything here probably will, because I've just been around enough of these. And so let's go ahead and test our theory here on the right-hand side. If we try +1, then 4 times 1 plus 23, and then we have +1 plus 6. This is totally working out. We're wondering if it's going to be greater than 0, and it looks like it totally will be, because 4 times 1 plus 23, that's 23 plus 4, 27 positive, and 1 plus 6 is positive. So this is 27/7 positive, and that is greater than 0. So that works out. So numbers on the right-hand side of 23/4 also work. So everything from there to there. Just not this stuff in between. That must be the only parts of the number line that actually make it less than 0, because these other parts make it greater. And so it looks like we have our solution set is looking something like, let's see here, from -infinity out on the left all the way to -6, parentheses, and then unioned with also parentheses, open circle, because there is no equal to on this greater than thing. We don't get to use equal to. And then from -23/4 all the way to wherever it is, infinity positive. And so then we're kind of just, let's see here. I'll go ahead and circle that mess. That's our solution set we're looking at, of things that actually do, when you plug them in, make this greater than 0. Some do and some don't, And then I just wanted to talk to you about how they want you to put your answers in. And so they want you to talk about two numbers, A and B, and we figured them out. A is the -6, and B is the -23/4. just because negative 6 is to the left on the number line, so I put negative 6 first and then negative 23/4 after that, because negative 6, the A part, they want to be less than B, so that means it's farther to the left on the number line. And then you got to pick which kind of an interval works, and we're saying, does it work from A to B? Did my solution go from negative 6 to negative 23/4? And it did not, because that was actually the part of the solution that wasn't working. That was everything we didn't want. It was actually the infinities that we wanted unioned with each other, but not having that in-between piece. So this A to B part, you're going to say no. And then from infinity to A, that's a yes, and from B to infinity, that's a yes, because that's these ones they're talking about. Kind of a weird way to say it, but that's what I wanted to at least kind of grind into your minds there. Anyway, that's all I got for now.